Welcome to uh, Design and Analysis of Algorithms, Dynamic Programming, Traveling Salesperson's Problem using Dynamic Programming Technique. Today, we will try to understand what is exactly a traveling salesperson problem is. As you can see, that a traveling salesperson problem is basically a traveling salesperson has to start from a native city, has to visit all the other cities once, and has to come back to its native city, or we can call this as source city. If we look at the same uh, uh, problem in the form of graph, you can see that the graph consists of each city in the form of vertices, and from one vertex to the other vertex there is an edge connecting, which generally depicts the cost of traveling. So there is a provision for a salesperson to reach to any other cities or vertices one at a time and then come back to the same city. So here, one of the major requirement is a traveling salesperson has to visit all the other cities once, which forms a circular path which encompasses all the vertices in the given graph, which we call it as Hamiltonian cycle. There can be more than one such kind of Hamiltonian cycle existing in the given graph. So traveling salesperson problem looks for an optimal Hamiltonian cycle which has total cost, traveling cost as minimum. If we look at this particular example, where we have 4 cities in terms of 4 vertices in a given graph, a traveling salesperson starts from any one of the vertex. So here in this case, a traveling salesperson starts from vertex 1 and reaches to vertex 2, 2 to 3, 3 to 4, and comes back to vertex 1. In the similar way, a traveling salesperson can also choose different options like vertex 1 to vertex 2, vertex 2 to vertex 4, vertex 4 to vertex 3, and then. So like that, there are multiple options. When we give 4 vertices in a graph, so as per the exhaustive search method, there are n minus 1 if n is the number of vertices. N minus 1 factorial is the number of uh, combinations which we can generate. So therefore, if the number of vertices increase, the order of complexity of this problem will also increase in n minus 1 factorial, or we can call this as n factorial order of growth, or factorial order of growth. If we look at the similar kind of problem in the form of graphical representation, if we start with vertex 1, reach to 2, 2 to 3. So if we start with vertex 1 has 3 options. So therefore there will be 3 subtrees. And if you choose any one of the tree, like either 2 or 3 or 4 vertex 4, then once again from vertex 2, there is 2 options. Vertex 3, there is 2 options. Vertex 4, there is option. And similarly, from vertex 3, in the second level, we have one option, that is either left over vertex 4 and then connecting back to vertex 1. Same way the other vertices. So this is a set of options available. When we try to plot its distance, we can see that whenever we have a choice, we look for the minimum. In the first, when we start from the source vertex 1, you can see that there are 3 choices. So we can opt any one of the path which gives us shortest path, shortest Hamiltonian cycle. In the same way, when we go to either vertex 2 or vertex 3 or vertex 4 in the next level, so we have 2 choices. So either we can choose any one of the choice to opt for, which has a minimal total coverage or minimal shortest path. So likewise, when we come to the third level, here we don't have much choice because we have only one option left out, so there is no much choice. So likewise, we can keep on identifying the best choice and then we can choose, and then that can lead to shortest path. But when we are looking at in this kind of solving technique, you can see that a problem like connectivity from 4 to 1 or 4 to 3 to 1 or 2 to 1 at the bottommost tree, these are all overlapping problems where even if you solve once, it keeps reoccurring, and in the exhaustive search method, all these problems have to be solved. Now, this sort of problems can be overcome in dynamic programming by selecting only those set of problems which need to be solved, where if the problem is reoccurring or overlapping, those problems can be suppressed from solving again and again. Now we'll move on to solving traveling salesperson problem using dynamic programming. So dynamic programming says that whenever we want to find out shortest path or shortest Hamiltonian circuit, so this Hamiltonian circuit is given in the equation of G, which is nothing but shortest path from vertex 1 to all the remaining vertices and coming back to the source vertex 1. So that is given in the form of when you have multiple options where uh, vertex 1 can connect to the other vertices. You can choose K as one of the vertex starting from 2 and try to connect to all the other vertices and connect back. So this can be done via with the help of C of 1 to K. That is nothing but cost of connectivity from vertex 1 to vertex K and shortest path from vertex K to remaining vertices. That is nothing but V of V minus 1 comma K. This can be generalized a little more, wherein G of I comma S, where I stands for the source vertex and S stands for the remaining vertices, that can be given as a minimum cost of C of I to J, that is connectivity cost of I to J, plus shortest path from G, that is J to remaining vertices of S, leaving J, that is S minus J. When we consider the first vertex, reaching back to the source vertex, so that is when we look back to our recursive tree, it means to say that it is the bottommost level of the tree. So we start solving the problems from the bottommost level of the tree. Why? Because there is more number of overlapping subproblems do occur at the bottommost of the tree than at the top of the tree. So therefore, we try to solve the overlapping subproblems which are at the bottommost of the tree, record them, and then start solving the next level to that with the help of already calculated last level solutions, and so on. We keep doing that. So in that way, when you want to reach to source vertex, so here that can be given as G of I comma null. That means to say that null here, it indicates none of the vertices are being acting as an intermediate vertex before I reaching back to source vertex. So in that case, you can see that G of I comma null indicates it's a cost of connectivity from I to a source vertex, which is nothing but vertex 1. So likewise, we can first solve all the sub-problems which are at the bottom of the recursive tree. So our solution follows in the similar way. As we can see here that we have a problem, 4 vertices graph, and each of this vertex has an outgoing edge and an incoming edge. That means to say that every vertex has an outgoing edge to every other vertices, and same way every vertex has an incoming edge from every other vertices available in the graph. So therefore, here in this case, it is a complete graph. So we are taking this complete graph and we are performing the traveling salesperson problem solution. So in the stage 1, we look at the bottommost of the recursive tree, that means to say that all the vertices will try to reach back to their source vertex. Or you can say that none of the vertices are being considered to be as an intermediate vertex before we are trying to establish a path to the source vertex. So that can be given as, if we consider source vertex as vertex 1, then we have a connectivity from vertex 2 to 1, we have a connectivity from vertex 3 to 1, and we have a connectivity from vertex 4 to 1. So vertex 2 to 1, that means to say that no intermediate path, no intermediate vertex. So therefore, G of 2 comma null, it indicates that null indicates no intermediate vertex, 2 directly connecting back to source vertex. So that can be given as C of 2 comma 1, that is cost of 2 comma 1. Cost of 2 comma 1 is 5. Same way, 3 coming back to the source vertex is given as G of 3 comma null. Null indicates here 0 intermediate vertex. So it reaches back to null, and its shortest path is given in the form of C of 2 comma 3 comma 1. Same way, G of 4 comma null indicates it is a connectivity cost of 4 to 1, that is given as A. So this is a stage 1 where no intermediate vertices are being taken care when we are reaching to source vertex from the other vertices. So it's a direct edge. We utilize this information for the next level, that is next upper level, where the next upper level stage we say that it is one intermediate vertex will be used to connect back to the source vertex. So here in this case, G of 2 comma 3 or set 3, it indicates that there are one element set available. Vertex 2 takes a path to a source vertex. Vertex 2 takes a path to the source vertex via vertex 3. So that means there is a connectivity from vertex 2 to vertex 3, then cost of shortest path from 3 to source. So that is given in the form of C of 2 to 3 plus shortest path from 3 to the source vertex. So that is given as 9 plus 6, which is 15. Similarly, vertex 3 also has an option to reach to 4 and then connect back to source vertex. So that can be given as G of 2 comma 4, which is nothing but cost of connectivity from 2 to 4 plus shortest path from 4 to destination. So likewise, we have other options also, like vertex 3 can take intermediate vertex as 2 before it can reach to its destination. So that can be given in the form of C of 3 comma 2 plus shortest path from 2 to destination. Likewise, G of 3 comma 4, which indicates that it is vertex 3 is taking now a vertex 4 as an intermediate vertex before it can reach to its destination. So therefore, cost of connectivity from vertex 3 to vertex 4 and shortest path from 4 to destination. Same way here too. So we have vertex 4 now. So vertex 4 takes shortest path via vertex 2, and similarly vertex 4 takes shortest path via vertex 3. So that is given in this form. So this is considered to be a second stage where we are taking the set to contain a single vertex, or in a very simple way we say that it is single vertex intermediate before the vertex or a city can connect back to its source vertex. Same way, the third stage here in this case takes two intermediate vertices before a vertex can reach back to its source vertex. So that is, in this example, you can see that G vertex 2 tries to reach to the source vertex via, there are two intermediate vertices, that is nothing but 3 and 4, set 3 and 4. So now when you have more than one vertices in the set, remaining vertices, that is intermediate vertices, then we get a choice. That is, either you can reach vertex 2 to vertex 3, C of 2 to 3 plus cost of connectivity from 3 to destination via remaining vertices of this set, that is nothing but vertex 4. In the same way, we can also have another choice wherein we can connect from vertex 2 to vertex 4, that is C of 2 to 4, plus shortest path from 4 to remaining vertices, that is G of 4 comma set 3. So when we can utilize already calculated value of G of 3 comma set 4, same way G of 4 comma set 3, which is available on the top of this slide, or which we have already calculated. So in this, we will try to choose the least one. Same way, vertex 3 also can have two intermediate vertex before it can reach to its destination. That is nothing but G of 3 connecting via either 2 or 4 before it can reach to its destination. So that, as we have more than one element in the intermediate vertices, so therefore we have a choice. That is, vertex 3 can connect to vertex 2, then shortest path from 2 to destination via vertex 4. So that is given as C of 3 to 2 plus G of 2 comma set 4. In the same way, instead of going to vertex 2, 3 can also reach to vertex 4, then 4 can take remaining vertices of the set, that is nothing but 2 comma 4. 2 comma 4 remaining vertices are vertex 2. So we will get cost of connectivity from 3 to 4 plus G of 4 comma set 2. So we get a minimum value. Similarly, we have another option. We have explored vertex 2 to remaining vertices, vertex 3 to remaining vertices, and similarly, we have vertex 4 to remaining vertices. That is in the same way given as connectivity from vertex 4 to vertex 2, that is C of 4 comma 2 plus shortest path from 2 to destination via the remaining vertices, that is 3. Plus another option where you can also explore vertex 4 to vertex 3, that is cost of connectivity, cost of vertex 4 to 3 plus shortest path from 3 to remaining vertices before it can reach to its destination. So that can be given in the form as we have calculated. Now we have completed stage 3. Then we move on to stage 4. If you just remember the recursive tree, we are going to the topmost level of this recursive tree. When you say the topmost level of the recursive tree, now if you are trying to reach to 1, starting from 1, so you have 3 options. Either you can go to vertex 2, vertex 3, or vertex 4. So therefore, we have 3 intermediate vertices before our journey reaches back to our source vertex. So our source vertex here is vertex 1. So therefore, it can be given as shortest path can be estimated based on either one of the 3 paths from vertex 1 to either vertex 2, vertex 1 to either vertex 3, vertex 1 to either vertex 4. So that is given as minimum of cost of connectivity from 1 to 2 plus shortest path from 2 to destination via the remaining vertices, that is 3 and 4. Same way, cost of connectivity from vertex 1 to 3 plus shortest path from 3 to remaining vertices before it can reach to its destination, that is 2 and 4. Same way, cost of connectivity from 1 to 4 plus shortest path from 4 to destination via remaining vertices, that is 2 and 3. So that can be given in this form, as we have already calculated G of 2 comma set 3 4, G of 3 comma set 2 4, G of 4 comma set 2 3, which we have already calculated. We will take those values and then utilize them in calculation. So we find that now the shortest path cost is 35. Now to figure out how exactly we got this, or to figure out what is exactly the shortest path which we have obtained, we can backtrack and try to identify. So we have solved that G of 1 comma set 2 3 4 can be given with the optimal solution, and C of 1 comma 2 are cost of 1 to 2 plus shortest path from 2 to destination via 3 and 4 vertices. Now if we try to expand G of 2 comma set 3 4, We get a solution that the best path can be connectivity from 2 to 4, then shortest path from 4 to destination via vertex 5. If we try to expand G of 4 comma set 3, so we get a equation of this. So when we keep on expanding that, so we get a path that C, cost of connectivity from vertex 1 to 2, cost of connectivity from vertex 2 to 4, cost of connectivity from 4 to 3, and 3 to 1, which forms an Hamiltonian cycle, which is an optimal Hamiltonian cycle. So this is depicted in the form of 1 to 2, 2 to 4, 4 to 3, and back to 1. So in most of these unidirectional edges, whenever we always end up with one optimal solution where if we don't have any clashes, we may end up with one optimal solution. So this is one of the example. As a recap, if we just look at back our dynamic programming solution. So we start with the stage 1 where no intermediate vertices. The vertices can directly, the set of other vertices apart from the source vertex can directly connect to the destination. In the stage 2, we have one intermediate vertex with which the vertices can reach back to the source vertex. In stage 3, we have two intermediate vertices before which a vertex can reach back to its source vertex. So whenever it is more than one vertices in the set, connectivity set, then we get a choice. We can choose the best path possible, that is least cost path possible. And in the stage 4, which is in the case of a 4 vertex graph, in the stage 4 is the final stage where a stage 4 starting from the source vertex, reaching back to all the remaining vertices, that is 2, 3, 4, and connecting back to the source vertex. So this can be given as 3 different options. We'll try to choose the minimum one. Using that solution with the help of backtracking technique, we'll be able to find out the shortest path from the source vertex to reaching to all the vertices and connecting back to source vertex. So this is one of the technique which will improve the the calculation of shortest path in comparison with exhaustive search. So it will try to solve only those subproblems which are appearing for the first time, and then it records its solution. And whenever overlapping subproblems reoccur, then it utilizes the already solved solution and then proceeds for the next steps. So this ends our dynamic